All right, we finally have a slightly shorter video for steps 4 and 5. And this is where we're going to talk about something called a p-value and writing a conclusion. So the most important thing for this video, well, I don't know, there's a lot of important things, is that the p-value is a probability of seeing our evidence or something more extreme. So, for example, going all the way back to how we started this, p-value is what's the probability of seeing our situation. So when we got 35 heads, we found that the p-value was 0.33%. Okay, so we've already found a p-value. It's just look at what happened with our evidence. We flipped the coin 50 times. We got 35 heads. What's the chance that would have happened? Or even something more extreme. So notice that we didn't find the probability that we got exactly 35 heads, but the probability that we got at least 35 heads. That's what p-values are going to be all about here. So there's kind of 3 ways of finding a p-value, and it really just depends on what your alternative hypothesis looks like. So something called a right-tailed test is when we use this alternative hypothesis. Left-tailed test with this alternative hypothesis, and a two-tailed test when we have a not equal to hypothesis. All right. And so the p-value is just the probability of that happening. So in a right-tailed test, if we're looking at this, the p-value is just what's the probability. And remember that standard z has mean 0 and standard deviation 1. What's the probability that a normally distributed random variable is at least our test statistic? And visually, right, it's going to look like this. That's why it's called a right-tailed test. The probability that we're bigger than something is shading something on the right. Left-tailed test, of course, will look very similar, but on the left. And two-tailed test is a little different because we have both tails. But we can calculate it by just using one tail and doubling it. We'll need an absolute value to force this to be positive. Two-tailed tests aren't very common for us, though. But this is the most important thing here. P-value is just the probability of seeing our statistic or something more extreme. So let's go all the way back to this example with a company trying to set up instructions for their smartphones. We found that our test statistic was about -2. Let's find the p-value. The p-value is just the probability. Ooh, which test are we using? Left-tailed, right-tailed, or two-tailed? What do you think? It depends on the alternative hypothesis. We have a less than. Which one was that? That's this situation. So the p-value is going to be the probability that z is less than our test statistic. So the probability that z is less than our test statistic looks like this. And we just use GeoGebra to calculate this. We go to a normal random variable. It's already standard normal. That's why we use z. Z is standard normal. We need to use the left. Here, let me zoom out a little bit so you can see. There we go. We need to use the left tail, so we're going to have to use this button, so it's shading on the left. And we want the probability that we're less than -2.04. What was it? Wait. 2.0412. Great. So that probability is about 0.02, about 2.06%. Whew. That's our p-value. You can write it as a percent or a decimal. I love percents, but decimals are fine too. That's how you find a p-value. It's, hey, wow, an actual short step for once. We've already done all the hard work. Finding the p-value is just one probability. And remember, z is standard normal. Mean is 0. Standard deviation is 1. And the p-value is just a probability that this happens. And now we're getting into the conclusions. If the p-value is small, we do one thing. If the p-value is not too small, we do something else. Just like with the fair coin example, right? We found it was really unlikely to have gotten 35 heads, so that made us suspicious. That was a very small probability, made us suspicious. A big probability would not make us suspicious. So let's formalize that logic. If the probability is really small, we reject the null hypothesis. Usually we phrase that by saying there's enough evidence to suggest that that assumption isn't true. There's enough evidence to suggest the null hypothesis isn't true. If the probability is not super small, then we don't have enough evidence. We'll usually phrase it something like this. There's not enough evidence to suggest the assumption is off. Now, small is a bit vague here. Okay? And it's because this probability depends on the context. We call it significance level. It's like the threshold. So if your significance level alpha is 0.05, if that's the case, then small is less than alpha. Less than a 5% chance. And not small is going to be bigger than or equal to 5%. So small just depends on your significance level, which depends on the context. In a stats class, we'll usually use 5%. That's the most common. But in general, you might see larger significance levels when the results aren't very important. Or if you're in medicine where the results are really, really important, it's really important that we're right, you're going to see smaller significance levels. Maybe you'll see a 1% significance level or something even smaller. For this class, just most of the time we're going to be using 5% unless the problem tells you otherwise. Just be aware that it does kind of depend on what you're doing. So let's finish up this video with a conclusion. If this is our common alpha, then which situation are we in? Are we small or not small? Is our p-value less than 5%? Yeah, it is. Right? It's less than 5%. So we're going to say it's small. What does that tell us to do? Oops. If it's small, we reject the null hypothesis. We say there is enough evidence to suggest the assumption isn't true. We do have to write it in the context of the problem. Well, let's look at this. There is enough evidence to suggest the null hypothesis is not true. How do we write the null hypothesis is not true? What does the null hypothesis have to do? Well, let's go back to the original problem. Right? Our null hypothesis was that 96% of customers are succeeding. Our null hypothesis, and maybe this is where the wording is more important, was that the company met its goal. Right? We were trying to test whether they failed that goal. So when we say reject the null, we're rejecting this. There's not enough evidence to say the company met its goal. We are rejecting this claim. Hypothesis testing is all about we have a claim, we take some evidence, we compare them. We are rejecting the claim. We wanted the company to meet its goal. We are testing to see whether it failed. We're rejecting the null. That's saying the company did not meet its goal. We know that their 94% was under the goal, but the company was hoping that that was just being unlucky. But no, we have conclusively enough evidence, statistical evidence, to say that you weren't just unlucky, you're really below that 96% threshold. There is enough evidence to suggest the company is not meeting its goal of 96% success on the instructions. And that's how your conclusion is going to look. This is the conclusion of your hypothesis test. This is really, really important that you word this non-mathematically. Okay, anyone can understand this sentence, basically. All right, all the math, all the work is also important, steps 1 through 5. But this right here, this is the big conclusion. And it's very challenging to write that because there's such confusing language. That's why the next video is just going to be us focusing on creating these conclusions. And it really kind of depends on how good your null hypothesis was. If you wrote your null hypothesis really clearly, and I was kind of lazy with this one, this really is a null hypothesis that's going to make this easy to write. You get a good null hypothesis. Oh, the null hypothesis is that the company met its goal. Then it's easy to either reject it or not reject it. So we got more practice coming up right for you in the next video. Let me know if you have any questions. And until then, bye-bye.